Good morning, DVCon. Welcome to day two. I hope you all had a great day one at DVCon. Uh, First of all, thanks to the organizers for giving me this opportunity. Great to be here. In the next 25 minutes, I'll be focusing my talk on addressing verification challenges for an intelligent and connected world. There is no doubt in our minds that we are at the age of 5G and AI. These two technologies are enabling us to connect billions of devices. These are generating massive amounts of data, and we're also powering new services at the edge. 5G brings in a lot of benefits that is listed in the slides. Extremely high efficiency, low latency, immediacy. It's also enabling new experiences and at the same time making sure that we have the privacy and security. So the next slide, what we want to talk about is the fact that the distributed intelligence is what is driving the future. So now everything used to be in the cloud. Now, given what we have from a 5G perspective, the intelligence and all the processing that is happening is also shifting from the cloud to the edge and on the device. So we are bringing the cloud closer to the devices at the edge. So the data from the industry shows that in the next by 2025, 62% of all the processing that is happening today will happen outside of the data center. So that's the data from an industry standpoint. So a combination of an edge cloud and on-device AI is going to drive the connected intelligent edge, right? And it also shows from a data perspective that 35% growth is what is being projected from a cloud standpoint. If that is what is holding good, then tremendous amount of edge cloud plus on-device AI is what is going to fuel the future. One of the industries that is going to, I want to talk about specifically is the automotive industry, which is going through a lot of disruption given all these technologies, whether it's in the telematics or in the connectivity, the infotainment, a lot of dashboards that are coming up, and with autonomous driving in the future with an ADAS perspective. So the car is no longer a mechanical transportation entity. It is an electronic transportation device, right? That's what the car is being transformed into. And this causes a lot of challenges from a chip standpoint, device complexity standpoint that we will talk about in the subsequent slides. So what we want to talk about right now is we have set the stage for how everything getting connected is happening. And that's now we will talk about what that means to the chip complexity. So 5G, automotive, XR, and IoT are all combining in single chip or multiple chips. So we are trying to put more logic in silicon to enable this connected world. But we're also doing that with a very compressed schedule. Everybody wants the device like tomorrow. And we also have forced to go to the new tech nodes. And the complexity of the use cases is increasing tremendously. And we all want this at the highest performance and the lowest power, which is causing a lot of challenge from a silicon development standpoint. And also, the early hardware software development is becoming a necessity if we have to have a silicon, because in this particular industry that we are in, there is no second chance, right? So this is requiring innovation from the process node up to the software development and everything in between, right? So what this is leading to is the intelligently connected world is leading to increased chip complexity. And we will talk about what this means to verification right now. So we talked about how the intelligent connected world is causing chip complexity to increase. Now we will talk about verification challenges, right? I mean, how this increases the verification challenge. So the first thing that I want to talk about is every company is going through this, right? At least from a Qualcomm perspective, we have multiple product lines and we need to have an architecture that is scalable. So before that, we wanted to be able to quantify what the complexity looks like. We will have various product lines in the company, right? And then each product line has its own complexity. And on the right side, I've listed a few things that we have used to compute the complexity. It might be a product use case. Is the first time IP or is it a lot of reuse? Do we have a new tech node as a stable tech node? What is the use case complexity? Is it a phone or an XR or an AR kind of an application? Do we have concurrent scenarios that are required for this particular chip? And what about low power? Is it a server kind of a chip or is it having a glass which has tremendous amount of low power requirements? So what we are seeing is one solution fits all is very difficult, right? But we do definitely need to have methodologies that are today scalable, right? So how do we do that? This is one challenge that we see from a verification perspective. This is a slide maybe shown in some of the previous conferences, but it is very powerful. So I just want to spend a couple of minutes on that. So we have applications that are going to all type of devices, starting from gaming to education. We have smartphone to automotive from a car perspective. So from a verification perspective, it is no longer enough to have the same test tube when you verify a particular use case for a phone. But what about the tablet? What about automotive, right? I mean, so this causes a lot of complexity as well from a verification perspective. Automotive is I want to call that out specifically. I think this is going through a tremendous disruption as I talked about, but it is also posing a lot of challenge for verification. So this particular graphic shows the current traditional verification outside of automotive, functional verification. You have systems requirement, there's a functional design that is derived, and then you do integration verification, which has code metrics, code coverage metrics associated with that. And then you have use case verification, which will be having functional coverage metrics. But from an automotive perspective, there are various safety mechanisms. So if you look at ASIL B as a requirement, you start off with a safety requirement, you need to do safety analysis, then you need to have a safety aware design, and then you need to know what is the target that you're having for a particular device that you're having. Is it an ASIL B or an ASIL D? Then from a verification perspective, there are multiple aspects here. So you have your regular safety feature verification, then you have mission mode where you need to run BIST as well as make sure that the mission mode is not impacted in parallel, right? Those things need to be done. Then you need to validate how powerful are your safety mechanisms. So fault injection becomes very critical. And in automotive, there is tremendous amount of value associated with traceability, right? Starting from your definition to your design, to your test cases, to how it is being validated in pre-silicon, post-silicon, the customers are demanding this. And if you extend this to ASIL D, which is the next highest level of safety, then it provides its own challenges with respect to diagnostic coverage from a use case driven perspective is very important. And also you need to have safety element out of context related fault campaigning, where the safety mechanisms that you are putting, you can have FMEDA, but you also need to measure that using the fault campaigning, which is very complex, but that is a must do from ASIL-D perspective. So overall, the automotive provides a great verification challenge that we need to kind of talk about. And we'll talk about in the subsequent slides what we can do about it. So in summary, from a verification challenge perspective, the connected intelligent edge is driving high level of verification complexity. We need to be able to quantify that. The use cases are growing. The new tech node provides a lot of complexity for MSIP and tech IP related validation. Security and chiplet, we didn't talk about in detail, but those are also another aspect that we need to look at. Automotive, we alluded to that. And then low power is a major problem that we have, right? So overall, these are some of the verification challenges, in my view, that we can think about. Now that we have talked about the verification challenges, I would like to talk about a few focus areas. I wouldn't necessarily call them solutions, but from a company perspective, these are a few of the areas that I believe will help us, going forward, or at least that's something that we are looking at. So the first thing is something that is scalable and portable from a verification environment perspective. The chart on the left side shows the complexity that we talked about. It keeps on increasing, but we cannot keep on increasing the resources that we have, right? We are living in a very competitive market. I'm pretty sure every company is going through that. So we need to make sure that we come up with certain methodologies that help us keep the headcount in check, but at the same time also provide us faster turnaround from a market perspective. So what we are thinking about is a evolving automation where you have a metadata where all the design specifications can be captured. And then we are envisioning something from a DB spec that is auto-generated from the design spec. And this whole environment is query-based. And ultimately, you get automated RTL that is generated, and also the test bench and the DB collaterals, including the test cases, the optimized regression, formal related collaterals, and also the functional coverage. And a self-checking system, right, is something that we are envisioning. Of course, this is not applicable to all the chips, but today we have a lot of reuse. We have a lot of chips that we do in the IoT market. So we need to be able to have some methodologies that are scalable across all of this, but also provide you a great advantage in terms of the NRE as well as time to market, right? So this is a scalable and portable verification environment that we are envisioning. The other aspect that we are looking at, that I'm pretty sure the whole industry is looking at right now, is higher proliferation of formal. So starting at the SoC level, we have a lot of integration features that we use formal for, and we also think about sequential equivalence connectivity, where you have two devices, which is from a technology porting perspective, design remains the same. Can we use formal methods to tape out faster? From an IP perspective, we are moving towards complete formal sign-off. I'm pretty sure industry is doing that, but that is something which is also an evolution that is happening. But formal also has its own challenges. We need to have the ability to develop a lot of flows, specifically for threat analysis from a security. A lot of keys are getting compromised. How do you prevent that? Formal property libraries that are being developed using formal from a low power standpoint and also from an automotive standpoint. On the right side, for example, on fault campaigning today, the runtimes are very high if you use traditional simulation. So can we use formal to augment it? And this also requires a lot of investment from a CAD perspective, EDA perspective, from a tools and methodologies, because formal provides a lot of scalability challenges today. So another aspect that we are looking at is formal obviously provides a lot of opportunity to improve the quality, and formal test bench framework can be generated. We use it for power verification, as simple as register verification and as complex as security threat analysis. We already talked about sequential equivalence. A lot of deadlock assertions today take a lot of vectors from a traditional simulation perspective. We believe that a formal is a great opportunity to be able to reduce the complexity, increase the effectiveness for these scenarios. From a formal sign-off perspective, we are moving towards some of the steps that we can think of to move towards formal complete sign-off is the partition, the design, and the test planning that is required. The models need to be developed. And then there are a lot of convergent management techniques that we need to be using from a bound analysis perspective. How to use abstraction models to look at the size challenges that we have, regression mode analysis challenges that we have. And also, we need to have formal core coverage, right, from a closure standpoint, so that ultimately we can look at formal as a sign-off perspective. One of the challenges that we see in formal is we need to be able to map formal to track the progress into a traditional milestones, right? So we can still look at mapping it into full milestones where you have the partitioning of the design, the test plan creation that we normally do for traditional simulations, the interface level checks, right? How do you use formal for that? Then from a close to RTL freeze, end-to-end checks, and how do you do bound analysis? And ultimately, we looked at, before closing the design and taping out all the coverage closure that needs to be done. So we believe formal is a great enabler, and as a company, we are focusing a lot on formal to solve some of our challenges. This slide talks about from an automotive perspective. We talked about automotive as an industry going through transformation. We talked about the automotive verification challenges. In this slide, I would like to comment on, from an automotive standpoint, a few of the things that that are being done in the industry today, and specifically from a Qualcomm standpoint. So there are safety monitor methods that are, first from a verification standpoint that is required to have, whether it is a memory or a register or a set of clocks. The mechanisms can be ECC, can be parity. From a clocking standpoint, it could be monitors. Then there are hardware BIST methods today, whether it is logic dependent LBIST mechanisms that we need to analyze and finalize for the chip. And if it is memory testing, we have MBIST mechanisms that can be run on the field. Once you decide on the methods and the monitor methods, you need to look at how we can do fault simulation. There are various methods to be able to do that. So first you do an FMEDA analysis, you take the design, we have the netlist that is available with the test bench, and then you'll be able to do a good machine simulation. And then you need to be able to do a fault campaigning to figure out when you inject certain amount of faults, are we able to detect that? And how do you able to measure these concurrent fault simulations and have a coverage report so that you can measure the FMEDA? And then it is a closed loop where you go back to the analysis and say, do I need to change something in my design? Do I need to put some more fault safety mechanisms that will help me close this loop? Sometimes it is not possible to put something in the hardware. So we are looking at the black channel safety method. So for example, we have chip-to-chip communication, which requires safety methods and safety applications to be running. But the link you can encapsulate using CRC so that you can still not be 100% white channel, but still you can ensure that you are able to do these safety methods when you cannot do something that is in the hardware. A couple of things that are not mentioned in the slides is the redundancy, where you have lockstep CPUs today. That help to, there is another safety mechanism that we try to use. Sometimes we also look at software-based, SBIST, software-based safety mechanisms, where you have software test libraries where functional patterns are being run and you can grade them. And just like we have BIST, you can replace them with functional patterns to be grading them, and then you can run the mission mode. So overall, automotive verification has a lot of challenges, but today from an industry standpoint, a lot of methodologies are evolving. And at a high level, we wanted to talk about some of these aspects. The other aspects that we are looking at, that is happening in the industry today is the traditional tester that we used from a DFT structural test point is going through an evolution, right? I mean, there is a strong need to make it scalable, and there is a strong need to reduce test cost. So some of the things that we are looking at is running, the DFT patterns in some of the traditional functional platforms that we have. So this hybrid environment is posing a lot of challenges. Starting from, you have to convert the DFT patterns into a functional sequence. So the entire management of a situation where some portion of the design is in functional mode and then you have test mode running across all the chips is posing a lot of challenges. How do you do SDF simulation pre-silicon in a functional and a test hybrid mode? You need scoreboarding to figure out the validity of the test that you are running. And there is functional islands, right, where you need not, when the test is running, you need to make sure that this functional island is not kind of disrupted. So from a verification point, test point, you have a functional test bench that is UVM based, that is very traditional, where you boot the device and you have high-speed I/O and drivers. But now you also need to integrate this test-related, structural test-related aspects and collaterals, which would require, given the size of the designs, if you're running one core structural patterns, and you need to be able to black box, you need to enable parallel simulation that is not traditionally care about for functional tests. And then you have a vector-based environment today, and you need to be able to apply those time patterns in this hybrid environment and still validate and sign off the design. And when the part comes back, you need to be able to bring up these and go seamlessly from a pre-silicon emulation to the test platform that we have, which is very highly scalable. So we feel in the future, this hybrid in-system validation is going to be a big challenge for all the organizations that are doing that. And we are currently embarking in this journey with good amount of success. The next thing that we would like to talk about is system level verification. We already talked about 5G, AI, all of these aspects, right, that are creating new use cases. So you have XR from a glass standpoint, we have 4K video as an example, and you have 5G. We see a 10x increase in the use case count. But these are also causing a 100x increase in the system use cases that as a DB engineers that we will have to kind of validate, because all these can combine for a lot of innovation and a lot of system use cases. So we see this as a tremendous amount of challenge. In the next slide, we will talk about what are we doing about it, right? So if you take any chip, you will have a lot of processing power labeled as CPU in a generic form, starting from a powerful ARM processor to a Tensilica for low power, from a vector processing for 5G using DSP, neural processors for AI, and then we have RISC processors for other computation. So we have all of these in a single chip, causing tremendous amount of growth, right, in terms of the addressable space. Then on the top, you have the scope. Traditionally, it was performance and systems was related to systems integration. Then we have concurrent use cases that are being enabled with camera, 5G, everything coming into place. Performance has to be validated in multiple platforms, pre-silicon. Use cases are exponentially exploding, and we are doing all this from a low power standpoint. Many of the applications that we have are enabling and requiring low power scenarios that are getting very, very complex to test. And on the right side, we have a lot of these features that are increasing day by day: triple camera, modem, audio, graphics, performance, and video. The other challenge that we have is we are requiring to have all of these test cases that are currently scalable from a DV standpoint. Then you run it in emulation. We want to be able to run the same in ATE and ultimately from a silicon standpoint. So we believe that the portable test and the similar standard with PSS is a great opportunity to be able to use that to scale it across all of the system verification flow that we have. So some of the use cases that we are kind of talking about is the triple camera where AI is built into it with, once you take the pictures, the best picture is selected, or you have phones that are having multiple applications, that can appear in a single screen. So all the system concurrency scenarios are requiring us to increase the amount of system verification tests that we are trying to do. And these are some of the solutions that we are trying to have. So, what else in the future, right? Some of the challenges that we see in the future is, listed here. EDA interoperability, I believe, is going to be is starting to be a big challenge. From a coverage standpoint, we have multiple tool vendors that are not playing together, right? So when we have to sign off a chip, that is becoming a challenge. Formal verification, we have multiple tools. Given somebody is good in low power, somebody is good in non-low power. How do you have these formal properties and these assumes and these constraints portable across these tools that we have is a big challenge. Functional safety are new areas that we are talking about. Even though we are signing off many chips from an automotive standpoint, I believe that we have a lot of ways to go, right, in terms of the scalability that is required to handle these huge chips. And when you go to autonomous driving L3, L4, L5, I believe that we are just scratching the tip of the iceberg, right? That is another aspect. In addition to hardware, software co-verification is at a very, very nascent stage right now in all our devices. Scalability is a perennial problem. We have 40% increase in the complexity of the devices that we are doing, but the EDA runtimes and the memory capacity is actually doubling, right? And that is causing a lot of challenge from a compute standpoint. Post-silicon validation tool chains are very weak from an industry standpoint. Everybody, I'm pretty sure, is developing a lot of these devices or a lot of these automations in-house, including Qualcomm. We see limited options available where we can take something that is failing on silicon. How do you be able to take that and go into a verification environment and debug faster? So that is some of the challenges that we are seeing today. And handling the architecture level specs, right? So today, outside of automotive, the traceability is very low. A lot of errors are happening where something is getting captured by product marketing. How do you make sure that that spec is traceable from spec perspective to the design, to the validation, to the sign off, to tomorrow, even from a validation standpoint? I think automotive, the rigor is expected as part of 26262. I think going forward, this will become a norm for even non-automotive chips, given the complexity that we are dealing with and the need from a quality standpoint. So these are some of the verification trends that we believe is going to happen in the future. So in summary, we talked about how the verification complexity is quantified, how that is a requirement to help us plan better. And we also talked about the diverse use cases are making our job from a verification point very, very challenging. The new tech nodes, right? And we don't have enough time to prepare for these tech nodes, a lot of model challenges from a verification standpoint. And then we are not even scratched the surface on chiplets from a mobile standpoint by 2025 is going to be a norm. How do you develop your verification to have this portable from security to chiplets? And automotive verification complexity is already high, and we believe that it is going to increase even more in the future. And to address some of these verification challenges, we talked about some of the focus areas. We talked about the need for a portable and scalable test bench. This is a requirement from reducing the NRE standpoint and also building a scalable org. And we talked about formal verification, which is going to replace a lot of the dynamic simulations that we are trying to do from an efficiency standpoint, from a quality standpoint. We talked about automotive verification methodologies, including fault campaigning for ASIL-D that is going to evolve. We talked about in-system BIST solutions, hybrid test solutions, which are going to take DFT plus functional in the same environment that is going to evolve. We talked about power verification is going to be, continue to play a major role where high performance and low power is going to be continue to be the norm going forward. We talked about system level verification and how PSS is going to play a key role in that, and call for action for the EDA vendors to continue to partner with all of the development community to help build scalable architectures, right? So that's what the summary of my talk is. I want to leave you from an automotive standpoint, which as a company we believe is going to evolve, transform the way we drive. Hopefully in India as well as we continue to evolve into level 3, level 4, and level 5. So in summary, I think we are in for a great ride from an overall industry standpoint. The semiconductor industry is at the cusp of another evolution given the evolution of AI and 5G. And I feel that it's a great time to be in the semiconductor industry. Once again, please have a great time in DVCon Day 2. And thanks again for the opportunity to address all of you and share some of the thoughts that we have from a Qualcomm perspective and my view perspective. Thank you. All the best.